The architects of the ASCII character set have structured it in such a way to simplify text manipulation in both software and hardware. These were key features back in the day, saving compute and memory, which were more of commodities. Rather than relying on text libraries that implement static case conversion tables in memory, we can instead perform optimized bitwise operations upon individual ASCII code point values. More specifically, flipping the seventh bit of letters inverts its capitalization. The Shift button on older terminal keyboards did exactly this, where it flipped the sixth bit of any letter typed on the keyboard, eliminating the need for complex circuitry. Note that this doesn't apply for any non-alphabetical character, as the QWERTY keyboard layout doesn't follow any mathematical pattern, rather just placing characters in optimized locations for human typing. As mentioned in earlier internationalization and localization videos, computers cannot inherently tell whether a code point corresponds to a letter, number, or symbol. All the computer sees is a numeric value. Character sets help computers determine what code point values correspond to letters, numbers, symbols, and control characters. There's a complication, however, when it comes to storing numbers in computers. Unlike everything else in character sets, a number can either be stored textually as a character code point or raw in memory for arithmetic operations. These two forms of storing numbers have their own application and are not compatible. A number character's encoded value in memory is not necessarily equal to the actual number. Thus, you cannot perform any arithmetic operations on them. Of course, this all depends on the character set and encoding methods employed. Typecasting is a method employed by software as a means to translate between these two paradigms. Once again, ASCII implements a mechanism to simplify text-based operations, this case being typecasting between numeric values and code point values. Rather than relying on text libraries to implement static conversion tables in memory, we can instead perform optimized bitwise operations upon individual code point values instead. The ASCII architect's placement of number characters was done in such a way where you can derive the numeric value by just looking at the four least significant bits of the code point. Do keep in mind that this character set typecasting optimization is on a per character basis. Typecasting first involves determining the numeric value of each individual base 10 digit of the number, then calculating the overall value. ASCII's numeric typecasting optimization can only be applied in the former portion of the typecasting process, though it's without a doubt better than not doing it at all. Teletypes are really the grandfather of textual interfaces for computers. They paved the way for digital terminals, which were inevitably emulated to run on consoles and desktop environments to this day. Understanding the original application and workflow of teletypes will set a good foundational background. Teletypes primarily acted as a human to human interface. Their use as computer interfaces were more so a niche second hand application. They were essentially text based telephones that allowed two operators to exchange things as small as short messages to entire multi page documents. These teletype machines were traditionally connected via serial lines, phone lines, or a combination of both through the use of modems. It was common for mailrooms of large companies and militaries to lease phone lines, so there's no need for dial up to establish connections. These essentially acted as fancy electric typewriters, where typing a letter prints on your local paper as one would expect, but would also send the typed character to the other person's paper as well. This works both ways, creating a dynamic where both operators appear to be printing on the same piece of paper. There are a variety of configurations for teletypes, though the most commonly implemented one is a full duplex connection. In this configuration, a channel exists for characters to be sent in each direction. Theoretically, both operators can type concurrently, as two channels are available for each of their transmissions. However, concurrent typing was avoided as much as possible to avoid confusing workflows. Half duplex connections also existed where there's only a single bidirectional channel of communication. In this case, data cannot be sent and received concurrently. These were not as common as phone lines, as they were full duplex consisting of a pair of wires. One way configurations also existed, where half duplex unidirectional transmissions took place. These were commonly used for stock market tickers, for example. One thing to note with these old teletypes is that there was no flow control or queuing. State machines were too costly and expensive to implement on traditional teletypes. Rather, both teletypes used a matching baud. In such scenarios, it would have to be configured appropriately so the terminals don't trip over each other's feet when printing. Teletype operators generally followed certain workflows and protocols with each other, raising great questions. How would the two operators communicate and synchronize with each other in their workflows? For example, how did an operator know when the other has finished their transmission? How would they know if the other side has received their transmission correctly? And how would the other alert for attention on the other end? Sometimes a single operator operates multiple teletypes for dispatch situations, for example. Control characters serve as control mechanisms. These are known as non-printable characters as they don't have associated glyphs. Rather than a graphical character instructing a teletype to print a character, a control character would instruct the equipment to perform some other non-graphical operation instead. The bell character would trigger a physical bell attached to the teletype to sound, to inform a remote operator of a transmission. The start of text and end of text characters would serve as formal mechanisms for operators to formally determine when text bodies start and finish. The inquiry was used as a mechanism to ask the other operator to respond with an acknowledgement or negative acknowledgement for error control or some other inquiry. Device control 1 through 4 are characters available for manufacturers to implement their own custom functionalities. There are many other control characters used in old legacy teletype systems, but we will not cover them as you get the idea. How were teletype operators able to type control characters into the terminal? Control characters did have their own separate dedicated buttons on many teletypes. Many other models also had control characters share keys with graphical ones. This latter method is what prevailed through history, so we'll focus on that. This begs the question, if both graphical and control characters share a key, how would an operator be able to explicitly select one or the other? A dedicated button named Control was implemented on teletypes for this exact purpose. Holding down this control button switches the keyboard to control mode, where the operator now has the ability to type control characters. This key has persisted ever since and is now standard on modern keyboard layouts. How is it dictated which keys on the keyboard correspond to what control characters? To answer this, we must understand how the control button manipulates the ASCII character set. The first 32 characters of the ASCII character set are control characters, with code points 64 through 95 mapping directly to them. If you notice, the code points of each of these characters are identical, except for the sixth digit. The control button allows for non-printable control characters to be specified by the operator when typing traditional characters, performed through a bitwise operation of the sixth digit. The ASCII delete control character is unique in that it is not present within the 32 code points of the ASCII character set, rather being at the complete end. ASCII delete character deserves its own section in of itself, as there's historical reasons for why it's the last character in the range. Remember that only the 6th bit is modified to specify control characters. Thus, ASCII question mark would be used in conjunction with the control key to specify an ASCII delete control character. The control key only applies to characters used to map to the various control characters. The control key does nothing for those that don't map to any control characters, such as these. There are various notations used to represent ASCII control characters, as they don't have any associated symbols or glyphs. One common notation is known as caret notation, which are heavily used in text-based environments. As a software developer or administrator, this notation will be the most commonly dealt with. In caret notation, the printable characters used in conjunction with the control keys are used, prefixed with a caret symbol. For example, end of text would be represented in a Unix text interface as caret C, most commonly used to send the foreground process a terminate signal. ASCII delete would be represented as caret question mark. Caret notation is popular for two reasons. First, you could represent long control character names with only two characters, being extremely compact. Second, it informs the operator exactly which character was used with the control key to produce it. There's no need for reference tables. Although caret notation is most commonly found in text-based environments, these are not native to teletypes. Teletype equipment do not deal with caret notations, rather it's more so a software implementation by device drivers, as discussed later. A more modern notation for control characters are control pictures, found in graphical environments such as IDEs. These are not really standardized as each application may have their own graphical representations of them. A terminal is simply a device or setup used to interface with a computer system. As mentioned, teletypes are primarily used for human-to-human interaction, though they also served as a perfect candidate for use as computer interfaces. A teletype connected to a computer system would technically be considered a terminal, with the teletype acting as a terminal to the computer. There were several limitations for using traditional teletypes as terminal interfaces for computer systems, most of which involving the display of characters. First, they had limited baud, around 10 to 15 characters per second. Second, they had a slow and difficult clearing of characters. Display refreshing would make applications such as Top or the Eye impossible on teletypes. The ED text editor made at Bell Labs was actually designed for use with teletypes, as it could only edit one line at a time. And lastly, they wasted a lot of paper along with the overhead of maintenance. These listed issues were not inherent limitations for their original application as human-to-human interfaces, because humans are slow at typing. Human-to-computer interfaces, however, are a complete different beast. Due to the limitations of teletype terminals, digital terminals in time overcame teletypes in popularity, eventually replacing them. These used digital screens, which eliminated the issues of teletype displays, making them a better application as computer interfaces. On top of that, their sole application was for use as computer interfaces, unlike teletypes, which were more or less morphed into computer interfaces. Note that because of these stark differences between paper-based and digital terminals, not all text-based applications are able to run on both. For example, it would be extremely impractical or at many times impossible to run things such as the top utility, which prints out a table of constantly updating system information to the user. The teletype couldn't keep up. Escape sequences are another complication that teletypes don't support, though that's saved for a later section. On the other hand, digital terminals cannot print over existing characters to create effects, such as strike-throughs and diacritics. As paper-based terminals were essentially all replaced by digital ones by the 1980s, software ever since pretty much assumes that the user is running a digital terminal and don't really care about teletype compatibility, as no one uses teletypes anymore. GNU Core utils, along with other text-based applications, for example, throw teletype compatibility out the door. Moving away from typewriter-based terminals, the keyboard and screen really became two separate devices in their own rights. These digital terminals still made heavy use of serial and phone lines. The keyboard transmitted raw ASCII code points typed, while the screen received characters to either display or take action upon. Traditionally, these would be cathode ray tube displays. For human-to-computer workflows, control characters specific to older human-to-human workflows are either no longer used or have lost their original semantical meanings. As digital terminals were specifically designed for a human-to-computer workflow, many of these older teletype control characters are simply ignored and not used. These essentially became available characters for software to apply their own semantical meanings to. Software such as the Unix TTY driver, communication protocols, file formats, and many others may have different uses for each of these available control characters. Moving back to the world of terminals, just know that digital terminals ignore many control characters specific to teletype, human to human workflows. Digital terminal keyboards still have the ability to transmit the full range of ASCII control characters, as software may interpret some of these as mentioned above. Control C used for killing a process in the shell, for example. When it comes to digital terminals actually displaying received text, it only operates on a select few relevant control characters, ignoring all others. As mentioned, many of them either have redundant or deprecated functionalities. In modern times, physical digital terminals are few and far between. Text-based environments are now dealt with through the use of terminal emulators running in a desktop environment. This allows for resizing of terminal screens and having multiple open at the same time with just a few clicks, eliminating the overhead of dealing with a physical terminal and cabling. Learning about classic digital terminals are important because their original behaviors and properties persist to this day through the use of emulation. It's important to understand that terminal keyboards and computer keyboards are two separate beasts entirely in terms of their operation. Teletype and digital terminal keyboards are much simpler devices compared to computer keyboards. Terminal keyboards transmit the raw code points of characters type. It's as simple as that. Computer keyboards are those that are actually connected to the computer locally as a peripheral, typically in combination with the display, which is also directly connected to the computer locally. These devices do not send raw code point values of typed characters, rather sending what are known as scan codes to the OS. The OS then maps these scan codes into key codes through the use of a table, which are then made available for applications for keyboard input. In the eyes of computer keyboards, individual keys have absolutely no relation to any characters or function whatsoever. Instead, each key is identified by a code rather than what's physically engraved on the key. All keyboards do is announce when and what physical keys have been pressed or released to the computer. It couldn't care less about what's actually engraved or printed on each of the keys. Insert, caps lock, F12, print screen, and alphanumeric keys, for example, are all just available buttons with associated codes on the keyboard. It's up to the OS and applications to apply their own meanings to each of these scanned codes, either being of those physically engraved on the keyboard for word processors or having them adopt another application, such as movement in a video game, for example. The OS receives these raw scan codes and translates them to what are known as key codes through the use of a table. Unlike scan codes, which only describe which physical keys have either been pressed or released, key codes instead represent actual alphanumeric symbols and various other functions such as shift and insert. Ideally, you would want this table to produce key codes that match exactly what's engraved on your physical keyboard. This is done by selecting the physical keyboard layout of your keyboard in System Settings or at Install, though usually it derives it automatically, and it just works most of the time. If you ever run into a situation where a specialized key doesn't do exactly what's engraved on the actual button, there may be a possibility that it's related to these specific details. This is all an extreme oversimplification of how keyboard input is dealt with, without going into the weeds of drivers, X11, and Wayland. Applications make use of libraries to retrieve key codes from the system. Although key code values have associated semantical meanings, they are still just numeric values. This means that applications don't necessarily have to abide by the standardized semantics, rather applying their own special meaning to key code values. This behavior really depends on the particular application, with many applications such as Notepad just treating key codes as is without any semantical reassignment. This creates multiple layers of abstraction regarding keyboard input and depends on a variety of factors we will not discuss any further. Terminal emulators such as GNOME Terminal or Xterm move terminal functionality away from physical digital terminals to virtually emulated ones. Despite the terminal keyboard and terminal display devices being emulated, its I/O is still the same as its physical counterparts, operating on raw code points. As all terminal input and output operate on code points, the terminal driver of the OS couldn't care less about whether a terminal is physical or not. When you type into an emulated terminal, a scan code will be sent from your keyboard to the OS, which will translate it into a key code. The terminal application will then receive and interpret these key codes. When Xterm, for example, receives a key code for a certain character, it essentially presses a key of the emulated terminal keyboard in the virtual world using a virtual hand. The virtual terminal keyboard then passes code points to the operating system's terminal driver, as if we were a real physical terminal keyboard. As for emulation of terminal display devices, text is either displayed on a window in a desktop environment, for example, or on a video console when your graphics card is set to text mode, for example. This is commonly used when bouncing between virtual consoles on Linux. Different terminal emulators emulate the properties and behaviors of different digital terminals throughout history. The most widely emulated digital terminal for Unix-based systems are the DEC VT series. Though other models have been emulated as well, they are no longer relevant to modern Unix-based systems, as they are quite rare. The Xterm application was one of the first terminal emulators. It's extremely versatile, extensible, and configurable in terms of its support of the DEC VT series of terminals, as you could select which specific model you want to emulate: VT52, VT100, VT102, upon other DEC VT models. Although Xterm can emulate the properties and behaviors of these older digital terminals, it's rarely done in modern times. Desktop environment-based workflows are more involved than traditional physical terminal-based workflows. Users demand applications to implement features such as mouse events, clipboards, hyperlinks, scroll buffers, upon many other desktop environment-specific features. These desktop environment-specific features were not present on older DEC VT terminals, for example. As a solution, the Xterm project created a new terminal mode called Xterm, ironically. Xterm mode inherits the baseline behaviors and properties of the original DEC VT series for backwards compatibility, though appends these desktop environment specific features on top of it. With the combination of the Xterm mode being backwards compatible with traditional DEC VT terminals, and the fact that it was really the first to implement desktop environment features, made the Xterm mode more or less a de facto standard to this day. The Xterm mode and its derivatives are used by almost all Unix terminal emulator applications, from GNOME Terminal to KConsole. Another limitation with strictly emulating these old digital terminals is the fact that there are many keys found on modern computer keyboards which are not present on traditional terminal hardware. The end, home, and insert keys commonly used in a desktop environment workflow, for example, are not found on traditional DEC VT hardware. Thus, you cannot use them when emulating old digital terminals. The new Xterm mode adds support for these modern keyboard keys. This support is enabled through the use of escape sequences transmitted from the emulated terminal keyboard device. Here's a list of some common escape sequences Xterm mode generates with modern computer keyboards. This support makes Xterm mode better suited for desktop environment workflows. Escape sequences will be discussed in further detail in a later video. Shift in and out characters were originally used by old teletype systems to alternate between text colors, typically black and red. This was done by physically shifting the ink ribbons around so the right text colors punched on the paper. With later advancements of teletypes, manufacturers instead had shift in and out control characters swap between different text fonts and character sets as a whole. For instance, multilingual teletypes existed where both Latin and Cyrillic characters could be printed through the use of shift in and out control characters. Shift in and out characters really became up to the manufacturer's discretion on how they should be implemented. Later on, it was common for digital terminals to implement pseudographics, which would have consisted of symbols and designs. The exact graphics used would be terminal specific, however, so the use of pseudographics by software hasn't really caught on and is not used. Note that it's the terminal displays that really apply semantical meaning to the shift in and out control characters, as they instruct the display to toggle between the default and alternate set of glyphs to print. Terminal keyboards are dumb devices, so typing shift in and out don't affect their behavior whatsoever. These shift control characters instruct terminal displays to print an alternate set of glyphs to the screen. As a result, only graphical code points are affected by this shifting functionality. Control characters do not have associated glyphs, so they are unaffected by shifting. Their semantical meanings do not change with shifting. Up until the early 1970s, there were still computers and teletypes that made use of 7-bit bytes. This clearly became a problem as 7-bit systems could not make use of the extended ASCII region due to the lack of an 8th bit. Rather than shift in and out control characters toggling between color or font modes, many 7-bit systems use these shift control characters to toggle the display between the legacy ASCII region and the extended ASCII regions, thus allowing the extended region of characters to be printed on a 7-bit display. Note that these addressability complications of the extended ASCII region do not exist on 8-bit terminal display equipment, as both ASCII and extended ASCII regions can be fully addressed using 8 bits. This shifting chaos and addressability only applies to 7-bit terminal display hardware. The architects of ISO's 8859 series of code pages took into account this functionality present on many 7-bit terminal displays and computer systems at the time, as ISO wants their standards to be as portable as possible. Due to the fact that shifting only applies to graphical characters and not controlled characters, the entire extended ASCII range will not be addressable by 7-bit terminal displays. This leaves large gaps of code points that cannot be used to display glyphs on the screen. This was a huge issue for character set architects as a whole for defining the extended ASCII region. Placing graphical characters at places where these old 7-bit displays cannot address is bad for portability. As the world was headed towards an 8-bit byte anyways, many character set architects said fuck it and placed graphical characters at those places anyways. This was the case for all Microsoft's code pages, as Windows and MS-DOS ran on 8-bit byte IBM PCs anyways. Although this approach would have worked anyways as the entire world moved to 8-bit bytes eventually, architects of the ISO 8859 series couldn't take this approach, as they needed to be portable with existing communications equipment at the time, including pain in the ass 7-bit terminal display hardware such as the DEC VT05. The ISO 8859 character set series architects cannot place graphical characters at places where 7-bit terminal displays cannot address for portability concerns with 7-bit systems. This created wastage of valuable code points in the 8859 series of character sets. As wasting valuable code points is sacrilegious, and the fact that these gaps cannot contain graphical characters, the ISO 8859 series architects decided to make the best use of these spaces by filling them with even more control characters. This new set of control characters found in the extended ASCII region are known as C1 control codes, while the set found in the legacy ASCII region are known as C0 control codes. As C1 control characters reside in a region of inaccessible code points for 7-bit terminal display hardware, how would it be possible to send 7-bit hardware C1 control characters? This is a great question. It was decided that escape sequences at through underscore are to map directly to these unaddressable C1 control characters. Escape sequences deserve their own section in their own right. They essentially allow normal text to take upon an alternate semantical meaning than just displaying glyphs on a screen. It's safe to say that 7-bit terminals are extinct and have been for a very long time. The 7-bit addressability complications and shifting chaos are really relics of the past, though provide great contextual explanation of why we have two sets of control characters found in many character sets, such as the ISO 8859 series, for example. With the advent of Unicode and advanced terminal escape sequences, which we will discuss at a later time, have largely made the shift in and out control characters obsolete, not used by modern software and applications at all, really. Due to this, emulated terminals running in desktop environments such as GNOME Terminal have no support whatsoever for this shifting functionality. By default, Xterm also does not support shifting. As Xterm acts as a historically accurate terminal emulator, it has options to enable customization of shifting behavior, interestingly enough. Digital terminals only interpret a small subset of ASCII control characters, ignoring all others for reasons mentioned earlier. These consist of text formatting characters, the escape character used for initializing escape sequences, and finally the bell character, surprisingly enough. Despite the deprecation of many control characters, bell somehow made its way to modern terminal emulators. What used to be physical bell on teletypes now causes terminal emulators to sound, even allowing you to customize its sound as Peter Griffin laughing, for example. Control character support can vary between different make and models of digital terminals, though they almost always support this configuration. The shown configuration was taken from Xterm and GNOME Terminal, which emulate DEC VT series hardware. DEC digital terminals are really the gold standard, and whose behavior is emulated in virtually all Unix terminal emulators used in modern times. As desktop users, our first intuition is that the backspace key removes characters behind the cursor, while the delete key removes characters in front of the cursor. At first glance, one may assume that ASCII delete and ASCII backspace control characters would behave similarly, though this is simply not the case. Typewriters had the backspace key move the printhead backwards one space, hence the name. These had some interesting applications. Backspace provided the ability to print over the same character twice, allowing for strike-through text, diacritics, bold, and other visual effects. Backspace did not apply any whiteout paste, however, so it never really removed any printed characters. As teletypes are essentially typewriters on steroids, they inherited this backspace functionality. Use of backspace enabled teletype operators to make use of these visual effects. Once digital terminals came around, they also inherited the backspace character. In digital terminals, they are only used to move the cursor backwards one space. Digital terminals do not allow for multiple characters to be printed over each other, as only a single character could be shown within a text cell at a time. Rather than printing over existing characters, digital terminals simply replace them. All in all, the ASCII backspace character instructs terminal displays to move their printhead or cursor backwards by one space. The ASCII backspace character does not inherently perform any text removal at all. Many teletypes designed or adapted as computer interfaces implemented punch cards or punch tape. This is very useful, as an operator can either record textual user input, terminal output from the remote computer, or both, recording an entire session. To play back the recordings, all the user would really need to do is feed the punch cards or tape back into the machine. A major application of these teletypes were solely to act as paper punchers for operators to store programs and data. In this mode, the terminal would not communicate with the computer at all whatsoever, acting solely as a paper punch. As you may have guessed, errors were problematic for these old teletype systems. Programmers and mailroom operators, for example, were prone to typing erroneous keystrokes to either be transmitted or punched permanently. Data corruption also existed, where erroneous bit flips would occur during transmissions. The ASCII delete character is used to delete characters, though there are several caveats to its use. Paper punchers were really dumb devices. All they did was punch code point values of characters into paper. They couldn't care less about whether they were graphical or control characters. The backspace control character would move the print head backwards a space, for example, though would not move the tape or punch card backwards, instead, literally punching in the code point of ASCII backspace into the paper. This actually was a pretty sweet feature, as punch tape could record taken backspaces to print over existing text, recording things such as strike throughs, diacritics, and bold. The same went for the ASCII delete character, as it would just be punched into the paper as any other character would be. To remove characters, when operators were using teletypes solely as paper punchers, they would have to manually reel the punch tape backwards to the erroneous character and punch the ASCII delete character, overriding the original punched value on the paper. The ASCII delete character needs to punch out all the holes of the original value, which is why it's the highest code point in the ASCII range. Now that the erroneous characters are overridden, anyone visually looking at the tape can clearly see that the characters with all their holes punched out represent erroneous characters that should be ignored. This begs the question, as ASCII delete is used to remove erroneous characters from the punched tape, will it also apply a whiteout paste on the typewriter itself? Some teletypes did, though in order for this to work, both the paper tape and printhead needed to be manually reeled to the proper position. Remember that we cannot use the backspace characters to reel backward, as these would inadvertently be punched into the paper. Due to the overhead and annoyance of having to reel two devices to the proper position to use the ASCII delete character, many teletypes didn't even have ASCII delete apply whiteout paste at all, eliminating this manual hassle. Of course, more often than not, whiteout paste would have its own dedicated button on the teletype or typewriter. After marking an erroneous character on the punched tape with an ASCII delete character, you would simply resume typing the rest of the string correctly after the error. If you realized that you punched an erroneous character in the middle of a large body of text, you were shit out of luck. Such situations require punch tape splicing to implement corrections, similar to editing old movie film. The punch tape reader is really a dumb device, transmitting the punched code point values for each character that it reads. It absolutely could not care less about whether it reads a graphical or control character, treating them all the same. The reading or playback of punch tape can occur in two ways. First being that the tape reader device outputs to the computer, acting as user input. The second being that the tape reader device outputs to the teletype display, acting as computer output. Let's now consider a situation where punch tape reader output is directed toward a terminal display. Erroneous characters are marked with the ASCII delete pattern on paper. Thus, whenever a teletype receives an ASCII delete character, it treats the received code point value as a no-op, performing no glyph printing or control character operations, continuing on to the next character to be dealt with. Teletype displays will also ignore the ASCII delete character from a computer, as teletype displays cannot tell or care about whether textual input is coming from punch tape readers or computers. A secondary inadvertent application of the ASCII delete character was for use as a flow control mechanism. As teletype displays treat ASCII delete character as a do nothing character, computer systems and old software back in the day would send ASCII delete characters to the terminal display intentionally, essentially stalling hardware in the name of flow control. The ASCII null character was more commonly used as a flow control mechanism, though we will discuss flow control more in depth later on. Digital terminals adopted many of the traditional teletype properties and behaviors, including the ignoring of received ASCII delete characters, treating them as no-ops. In addition to the digital terminal's treatment of received ASCII delete characters, it also treats all other control characters it does not interpret as no-op characters. Generally, characters that are specific to human teletype workflows that are no longer supported on digital terminal workflows. As the world moved from teletype terminals to digital terminals, paper tape and punch cards became obsolete, as data began to be stored on file systems instead. The tedious process of character removal involving punched paper and typewriter displays did not apply once the world moved to digital terminals. As data became stored on file systems, there was no longer a need for ASCII delete character to mark erroneous characters, as corrections could be made on the spot through the use of basic file system operations such as open, close, read, and write. The process of removing characters simplified once the world transitioned to digital terminals, as we don't have to worry about manually reeling paper punchers and typewriter heads in order to apply corrections. When digital terminal displays write to a cell on the screen already containing a character, it simply replaces the original character with the new one. This unique property is exploited for the removal of text on digital displays, simply through writing over existing text on the screen. More specifically, writing space characters over the existing text to clear stuff on the screen. As digital terminals in general are dumb devices, the removal of text on digital terminal displays requires software on the computer to strategically control the terminal cursor, writing the correct characters to select positions on the screen. This is typically either done by the operating system's terminal driver or user space applications, as we will discuss in a later video. In essence, the responsibility of text removal shifted from manual operator intervention to software logic. As the world transitioned to digital terminals, a serious issue arose. How would a user signal that they wanted to remove a character off the screen to software? Should the user pass an ASCII backspace character to the computer? ASCII backspace's traditional semantics are to move the typewriter printhead or cursor backwards by one space. This really has nothing to do with any text removal at all. What about the ASCII delete character? Should the user pass an ASCII delete character to the computer? The ASCII delete character's sole purpose is to punch out all the holes on paper tape and punch cards. Punch cards and tape are now obsolete, with both teletypes and digital terminals treating ASCII delete as no op or do nothing characters. Here, we must make a clear distinction between computer bound and terminal bound character semantics. Control characters sent from a terminal to a computer may have different meaning if it were instead sent in the opposite direction. The semantics of characters sent to a terminal display are dictated by terminal hardware. On the other hand, semantics of computer bound characters are more subjective, as it really depends on what software is running on the computer. More specifically, the software dealing with terminal I/O, whether this be a user space text based application or the operating system's terminal driver. Each of these softwares may apply their own unique meanings to individual computer bound characters. ASCII backspace and delete's traditional semantics are only really applied when sent to terminal display hardware. ASCII backspace, delete, and all other control characters are inherently meaningless when transmitted from the terminal keyboard to the computer. As a result, they are available characters for software to apply their own custom semantics to. The Unix terminal driver has a list of special terminal characters that perform various actions. Characters received from a terminal keyboard device can be assigned the semantics of any of these listed functionalities. For example, by default, the ASCII negative acknowledgement character is designated as having erase line semantics, though erase line functionality can optionally be reassigned to another character instead if an administrator so chooses. The real important special character is the erase character, whose semantics are by default assigned to the ASCII delete character. That's actually an extreme oversimplification, though we'll save that for a later video. This erase functionality is responsible for text deletion on terminal displays, essentially acting as a modern desktop environment backspace, removing characters behind the cursor. When a character sent from the terminal keyboard triggers this erase functionality, it deletes the character behind the cursor on the digital terminal display. It does so by replacing text with the ASCII space character, which has an empty glyph. This creates the illusion that text has been removed from the text cell and nothing is here. In reality, whenever you see any empty space on a digital terminal display, it's actually just a bunch of printed graphical ASCII space characters. This creates the illusion of empty space. Specifically, the erase functionality emulates the desktop environment backspace behavior through the use of printing the following string of characters to the terminal display. As the world transitioned to digital terminals, there became ambiguity between ASCII backspace and delete characters on terminal keyboard devices. Some digital keyboard models have keys engraved with backspace actually send an ASCII delete character, while other models simply send ASCII backspace. Ambiguity also existed with keys engraved with delete, where the button either sent ASCII delete, ASCII backspace, or an escape sequence. The wide range of behavior between digital terminal models primarily stems from the fact that software such as the terminal driver allows for administrators to reassign computer bound characters to different semantics. This ability abstracts away model specific differences, though it is extremely annoying to constantly change settings each time you want to bounce between different terminal models. As we know, the DEC-VT series is really the gold standard for terminal behavior on modern Unix-like systems. Its treatment of the backspace and delete keyboard keys are most important to know about, as DEC-VT terminal behavior remains dominant to this day. On DEC-VT hardware, the key engraved as backspace actually sends an ASCII delete character, while the key engraved as delete sends the computer an escape sequence, funny enough. The days of constantly fussing with software settings each time you bounce between terminals are over, primarily because all terminal interaction on Unix like systems nowadays are all DEC-VT based. Despite modern terminal emulators on Unix being DEC-VT based, many still have compatibility settings that allow you to customize the backspace and delete key behavior. The horizontal tabulation control character instructs textual displays to perform horizontal tabulation. Each device displaying text may implement tabulation in its own way. For the case of typewriters, the amount of space that horizontal tabulation consumes can be configured with an adjustable stop. For teletypes, different make and models may have different standards for how much space horizontal tabulation consumes. For the display of files in modern times, word processors let the user adjust indentation spacing in documents. Text editors and IDEs let you adjust how many space characters these horizontal tabulation characters consume. In summary, how far text is visually displaced is really implementation dependent, as this visual displacement is merely just a mechanism to convey to the user that an ASCII horizontal tabulation character exists in the first place. Despite DEC-VT terminal behavior being a gold standard on modern Unix, it's extremely rare for modern text-based utilities to print this horizontal tab to the terminal display. As horizontal tab behavior varies so much, the utilization of spaces are preferred. I'm in firm support of team spaces in programming. Vertical tabulation will be discussed later on when discussing Newline. The ASCII carriage return character was adopted from old typewriter functionality, where the printhead would slide back to the beginning of the paper. The primary application of this functionality was to physically slide the printhead back to the beginning of the paper when you needed to continue printing on a new line. This functionality was emulated in digital terminals by moving the cursor to the left side of the screen. As printing over existing text on a digital terminal replaces the already printed text, carriage return enables loading bars, timers, and other information to be printed on the digital display in real time. ASCII line feed is equivalent to the action of physically scrolling the paper down a line on the teletype. On teletypes, this ASCII line feed character would cause the paper to be scrolled down a line through the use of an electric motor. As scrolling the paper only moves the printhead vertically, ASCII line feed character is typically used in conjunction with the carriage return control character, as we will discuss later on. Digital terminal displays emulate teletype line feed functionality by moving the cursor down vertically by one text cell. ASCII form feed, also known as page break, instructs teletypes to eject whatever paper it has printed on thus far and resume printing on a new page. This form feed functionality enabled the pagination of teletype paper scrolls. In other words, the process of dividing a single scroll of paper into multiple pages. Teletype paper ejections either took place through the use of a mechanized blade or just scrolling the paper far enough to create a page's worth of empty space. This functionality is simulated on modern digital terminal workflows. Instead of ejecting paper, text shown on the screen is simply shifted upwards in the text buffer past the screen, creating the illusion of a new page. As you scroll up in the terminal's text buffer, you will find the text that was supposedly ejected off the screen. DEC-VT hardware doesn't inherently support the form feed pagination functionality. Printing a form feed character to a DEC-VT terminal is pretty underwhelming. Instead, pagination functionality is implemented by user space software rather than the terminal itself. When a user presses Ctrl L while operating a shell, for example, the form feed character is passed from the terminal keyboard device to the shell program. Shells typically use text buffer libraries such as GNU Readline to handle terminal interaction with the user. The shell's text buffer would then translate this form feed character into a series of escape sequences to then pass onto the digital terminal display, instructing it to move its cursor to the home position, move its text buffer past the screen, and finally print a fresh shell prompt. As you can see, this simulated form feed pagination behavior really depends on whatever user space program is processing your terminal input. In this case, GNU Readline is handling it. Newline is simply an action that can be performed by textual display equipment. Newlines are embedded inside streams of text through the use of in-band signaling with control characters. They instruct textual displays to continue printing at the beginning of the next line on the screen. Textual displays include teletype paper printers, physical and emulated digital terminals, text editors, web browsers, and just about any GUI-based application that displays text. Different operating systems and textual display methods have their own definitions of how new lines are represented in streams of text. Some may say that new line is represented by one control character, while others may represent new line with another control character. Conventions also exist to represent the new line action in streams of text with a select sequence or combination of multiple control characters. Multi-byte new line conventions are used by Microsoft products, for example. To perform the new line action on teletype terminals, the printhead or carriage would have to be reeled back to the beginning of the paper, and we would have to scroll the paper down by a single line. These two actions would be performed by passing the teletype an ASCII carriage return character, followed by an ASCII line feed control character. Thus, for paper-based textual display methods, new lines would be represented by a carriage return, followed by a line feed, within a stream of text. As the printhead is moving diagonally relative to the paper, it doesn't really matter the order in which these two characters are passed to the teletype. As digital terminals emulate the behavior of traditional teletypes, digital terminals also require both a carriage return and a line feed to perform a new line action, though traditionally the convention is that carriage return is sent first, followed by the line feed, for reasons that we will discuss soon. In the past, memory, compute, and bandwidth were valuable commodities. Every byte of memory had to be utilized as efficiently as possible. In files, new line sequences induced significant overhead in terms of memory consumption, as each line of a file required control characters to represent them. Ideally, we would want to reduce this overhead as much as possible by representing new lines with single characters rather than sequences of them, as Microsoft's products do. Multics was the predecessor to Unix, which represented new lines in files using single characters rather than sequences of them. As a result, all Unix like systems today represent new lines with single characters. Multics had to choose which ASCII control character was to represent new lines, with the two main candidates being ASCII line feed and carriage return control characters. Theoretically, it could have been many of the other ASCII control characters, though line feed and carriage return made the most sense as new line characters. Other characters, such as the ASCII acknowledgement character, are not remotely related to new line functionality at all, where carriage return and line feed are. Although carriage return was a valid candidate, it already had plenty of specific usages, more than line feed. Carriage return, along with backspace, enabled several visual effects on paper-based displays such as bold, diacritics, and strike-throughs. Carriage return enabled digital terminals to display real-time information and things such as loading bars. As a result, Multics chose ASCII line feed as its new line convention and persists on Unix-like systems to this day. Interestingly enough, Apple used carriage return as its new line convention, though Mac OS eventually migrated to line feed once it adopted a BSD-like interface. Honestly, this move was for the best, because carriage return is so fun to use when programming. Many different textual display devices have differing new line conventions. For example, digital terminals require both a carriage return and a line feed character to move the cursor to the beginning of the next line. Passing just a line feed character itself simply moves the cursor down vertically, but not horizontally. Paper-based displays require both a carriage return and line feed character, in addition to flow control padding around the new line. Without this flow control padding, characters would be printed to the paper while the carriage is moving, creating a large, ugly smudge of ink on the paper. Some really obscure teletypes also perform an automatic carriage return upon receipt of a line feed character, though we won't have to worry about this as these got lost in history. Multics, which paved the way for Unix, was a driver-based system. Drivers abstracted away hardware-specific details. This includes the various new line conventions found between textual display hardware. This creates a more unified environment where a single new line convention can be used across the system, while terminal device drivers translate them to hardware-specific new line conventions, whether those be a particular individual control character or a specific sequence of them. As we know, Microsoft products are less abstract than Unix-like systems. This is pretty self-evident as Windows cannot run on anything besides IBM-compatible x86 machines and recently, select ARM configurations. Unix, on the other hand, has implementations for just about every instruction set architecture. Back in the days of MS-DOS running on traditional IBM PC, AT, XT, and clone hardware, things operated less abstractly. Applications were able to talk to the hardware directly using IBM's legacy memory mappings and devices. This included talking directly to BIOS to perform various actions without the need for drivers. As things are more hardware bound, it's only natural that the new line convention be a sequence of carriage return and line feed. Such sequences were often required when talking directly to hardware to print text. Without the abstraction provided by device drivers, new line conventions are less portable. Unix terminal drivers enable support for a wider range of textual display methods through the use of abstract drivers. As history progressed, we are now left with essentially two new line conventions left in the world: Unix's line feed convention and Microsoft's carriage return plus line feed convention. This creates compatibility complications when moving files, scripts, and terminal output between the two worlds. As far as displaying Microsoft new lines on a Unix terminal, you should be good. You'll just end up with an extra carriage return character that doesn't really affect textual output at all. Interestingly enough, for displaying text, the Windows console and Notepad applications interpret the line feed character as a new line. This is interesting because Windows new line convention is a combination of both carriage return and line feed. As Windows console and Notepad only really interpret the line feed character as a new line, the carriage return is just an extra redundant character. This is similar to how Unix terminals treat Windows new line conventions. Many text editors, such as Notepad and VS Code, allow you to configure new line conventions. This likely won't really affect the display of text, but instructs the application what bytes to write to the file when you press the Enter key on the keyboard. In summary, when moving data between systems, be mindful of the fact that there could be some compatibility complications regarding new line conventions. In programming, C-style escape sequences are more or less standard across almost all languages. They allow programmers to specify control characters through the use of typable graphical characters. \n is really just a notation for the new line convention of your system. Printf, for example, will translate \n to a line feed, carriage return, or whatever the new line convention is on your system. The C-style new line escape sequence provides programmers everywhere with an easy-to-use and portable methods for representing new lines. In addition to the ambiguity between backspace and delete present on digital terminals, there's also behavioral differences of the enter key as well. Some digital terminals send the ASCII line feed character to the computer, while others send the carriage return instead. It really depends on the make and model. For the case of DEC-VT hardware, the enter key sends the carriage return character to the computer. As DEC-VT behavior is emulated on modern Unix, this property is found everywhere. As with backspace and delete, the terminal driver can be configured to settle the ambiguity between line feed and carriage return. The terminal driver has an input flag that treats the receipt of carriage return characters from the terminal as if they were line feeds. Unix's driver abstraction allows the system's new line conventions to be translated to hardware-specific conventions. Using line feed presents an issue on Unix systems, however. What if a program only needs downward vertical movement of the cursor or printhead and not horizontal movement involved with new line operations? The issue is that if our program attempts to send the terminal display a line feed character, it will be interpreted as a new line by the terminal driver and translated into a hardware-specific new line convention. This means the terminal driver could possibly insert a carriage return character, causing unwanted horizontal movement. DEC-VT terminals support the ASCII vertical tabulation control character. Traditionally, vertical tabulations involve an arbitrary amount of typewriter or teletype paper scrolling. Digital DEC-VT terminals happen to treat vertical tabulation as line feed characters, simply moving the cursor down a space vertically on the screen. Because the terminal driver does not interpret ASCII vertical tab as a new line, it will be sent unmodified to the digital terminal display. As a result, user space programs could theoretically perform line feeds without the line feed character tripping up the terminal driver. This practice is highly discouraged. There is no guarantee that every single digital terminal treats vertical tabulation characters as line feeds. Some may apply more vertical travel of the cursor compared to others. Despite DEC-VT digital terminals being a gold standard on modern Unix, it's still bad practice in terms of portability. Thus, it's rare for text-based utilities to make use of vertical tabulation characters. Generally, as an alternative, programs either make use of escape sequences or set the terminal driver to raw mode. Raw mode sends characters straight to the terminal without any interpretation or modification. This feature will be discussed in later videos. Null characters are those that have none of its bits set. As new fresh punch cards do not have any holes punched in them yet, all of its characters are by default null. The same can be said for zeroed out text in program memory or files. Terminal hardware treats the null character as a no-op character, performing no action whatsoever. The terminal display simply waits for the next character to deal with. This is actually the same as how ASCII delete is treated by terminal displays, as mentioned earlier. This control character was the most common flow control mechanism used for old paper-based teletype displays, intentionally stalling the printing of characters. A great use case for flow control on older teletype systems are for new line operations. As we have mentioned earlier, line feeding carriage return operations may take a relatively long time to perform compared to printing of individual characters, as these teletype printheads had a lot of mass and inertia. This may result in the printing of characters while the printhead is still traveling, smudging the paper. Unix terminal drivers, for example, would have to include null characters and teletype new line conventions. This intentionally delays the printing of characters until the printhead travel has finished. As null is treated as a no-op, operators can arbitrarily insert these null characters into programs and data stored on punch tape without inadvertently affecting anything. When punching programs into punch tape, it was common for programmers to insert large spans of null characters in their code. This lets them modify these areas of space in the future, where programmers could go back and punch in additional instructions or data at a later date. This allowed for programmers and operators to not be burdened as often with the chore of punch tape splicing. As programs and data are now stored on file systems, modifications can be made in place without the need for punch tape splicing and large spans of null characters in source code. In matter of fact, in modern times, it's quite possible that the inclusion of null characters in a program source may break it, though this all depends on the language, compiler, or interpreter's behavior. People often confuse ASCII null character with the ASCII space character, even though they are not the same. First of all, ASCII space is considered a graphical character with an associated glyph. Graphical characters instruct terminal displays to print glyphs to the screen, moving the cursor forward afterwards in preparation for the next character to print. ASCII space is considered a printable graphical character, despite the fact that its corresponding glyph is just empty space. Digital terminals traditionally have bitmapped fonts. Because ASCII space is considered a printable graphical character, it has an associated glyph bitmap, just like any other character, and is printed on the screen just like any other character. Though because it's a space, its bitmapped is zeroed out. Emulators such as Xterm still make use of bitmapped fonts, though more modern terminals such as GNOME Terminal or KDE Console have moved away from that. Null is considered a control character and not a graphical character. As a result, absolutely no glyphs will be printed to the screen, and the cursor will not be incremented forward because nothing will be printed. It's extremely rare, but some terminal hardware, old and new, may actually print the ASCII space upon receipt of a null character in its place, which is extremely improper. This is rare, but if this is ever the case, there may be settings to change this behavior. One of the most popular applications of null in modern times is its use as a string delimiter in many languages such as C.